All right, so now we're recording, and I'm going to go ahead and share this screen with you. Here we go. So in the reading, there's a couple things that I wanted you guys to know, and I told you to focus in on definitions and stuff like that, curve fitting, and equations. And so just the couple of notes that are really important in our first section here is just the difference between an independent and a dependent variable. Are you familiar with those, or did you feel like you needed to refresh on those?
I'm familiar with those.
Alrighty, so just as that reminder, the X values on the X axis are going to be your independent, that's what you're controlling, and the Y values, what goes on the vertical axis, are going to be the dependent. They're responding to change. So when we're talking about our graphing activity here, the second column is going to be your Y values, and the first column is going to be your X values, or dependent and independent. So that matters because it depends on what kind of graph you end up with. So then they just give you an example that because you adjusted temperature, the volume goes on the vertical axis. That's all this section is showing you. So the first one we really need to pay attention to is this idea of curve fitting. So it says that the process of matching an equation to a curve is called curve fitting. And that's the process that you just said that you weren't sure about, is matching the equation. It's trying to figure out, what do I do? Why is it 1 over v? And so you're going to have a checklist. And I'm going to give you the checklist, and it's a pretty clear checklist. You're going to ask a question, and it's a yes or no answer. If it's yes, you go one way. If it's no, you go another way. All right? And it's just a flow chart. All righty. And if you want me to type it up, or you want to write it down, you're welcome to. But it's literally a flow chart on what to do first. So the big takeaway from this next paragraph is this equation right there, which is your slope-intercept form. So hopefully you're familiar with that. You should have seen that in algebra and geometry. It is the probably one of the most common equations you use in math. And so all this states is that any output, or y, is going to be equal to a change in the function, which is the slope. That's your rate of change, your rise over run, or your change in y over change in x. It's the rate at which this line changes position, where it is, at some point x. So when you put the x, that means for some input x, if you know the change of that function and where you started, you'll know the output. All right, so the example I give is if you know you're walking, 10 feet every second, and you start at 0 feet, so b is 0. If I tell you, you've been walking for 3 seconds. If you walk 10 feet every second, how many feet have you walked?
I'm sorry, can you say that one time? You're kind of breaking up.
Okay, so
Sorry.
give me just 1 second. I'm gonna move my everything so that I can plug into the Ethernet cord.
I heard the 10 feet, but I didn't hear what you said after that.
So if you walk 10 feet per second, so every second you're walking 10 feet. So that's also called running. So if you're running at 10 feet per second and you walk for 3 seconds, how many feet have you gone?
30 feet.
Exactly. And so what you just gave me was y. 10 feet per second is the slope, or the m, and then the 3 seconds is the x. And so really what this does is I just gave you a scenario and you predicted the future, right? So that's what the point of this entire assignment is to be able to predict what comes next in a graph. So can you hear me any better?
Yes, sir. I hear you good now.
Awesome, because I just connected to that Ethernet. For whatever reason, the outlet I was using was not working. So let's keep going. And a linear line is exactly what it sounds like. It's a straight line. Your goal is to always have a straight line. So I'm going to remind you that in order to have a slope, the line must be straight. And hopefully you remember that a curved line has infinite numbers of slope because it's constantly changing. That's why it's a curve. All right, and then they just remind you. So I just want you to notice that you had the form y is equal to mx plus b. And then they just slightly change that here, and they replace what's on the x-axis down here with t there, and they replace the velocity, or the v, with y. So that is going to change the form, but the basic structure is the same. You're just replacing variables with whatever shows up on your columns. All right, and then we get to the first example. Now I want you to notice that this is actually the same variables that you have. Hold on, let me move this to the bottom. Here we go. It's the same variables that you have here. And so this is the same data set. And I'm going to tell you right now, they're showing you the graph of the original data. So if you were to copy that, you'd be exactly right. But I want you to notice one of the trends in this data set. So the first question you ask yourself, I told you I'm going to give you a checklist. The first question you ask is, are both data sets moving in the same direction? What I mean by that, are they both increasing? Are they both decreasing? So if they're moving in the same direction, then you're going to know that it's not inverse. Okay? Because what inverse means is that as one goes up, the other goes down. It's seesaw action. So if one end of the seesaw goes up, the other must go down, and it's going to be back and forth. And the graph for inverse motion or inverse function is always going to look like this L right here. All right, it's always going to look like this curve, because if you look graphically, as this volume value on the x-axis goes up, the pressure decreases. And the only way to represent that graphically would be this curve right here. So when I go to number one, the very first chart that I've got here, the very first graph is going to be right there. So I'm going to have pressure here and volume there. You following so far?
Yes,
Right,
sir.
so this is just graphing the data. So that should be the first thing you do. And now the statement at the top of this piece or this assignment says that you have to recognize what kind of function. And I think that's where you said that you got stuck. And so you've only got 4 options. So I'm going to switch really quickly and just show you those 4 options. So this one you will start to recognize just by the shape or by the data. If you see it going up and down, if one goes in the opposite direction, it has to be inverse. So your first question is this an inverse function? If the answer is yes, you're done. You know it's inverse and you can start working with the inverse. If your answer is no, you continue to the other 3 options. So they take 1 over v, and I'm going to get back to that. So I just want to let you know I will be back to why it's 1 over v, because that was your question.
Okay.
But your other options are going to be 2 other kinds of curves. And they're both going to start somewhere around the origin. You're going to recognize that this one does not have an intercept, right? It never touches that y-axis. And if you've had chemistry, you know if you don't have volume, you won't have pressure. So there should be no intercept there. Now here, you've got distance and time. So this is described as a top opening parabola. So you should be able to recognize a parabola as a squared function. And it's top opening because it looks like a cup, right? It kind of looks like it's opening toward the top. So when you see this, so one of the ways of explaining this that I found really worked for students is to use a ruler. All right, so I've got a ruler here, right? So this would be flat, that's your x-axis, that's vertical, and a linear line will be at an angle like this, right? So how would I get this ruler to kind of bend to go up toward the y-axis? What am I going to have to do to the ruler physically?
You're gonna have to move your hand up.
So I'm going to have to pull on it, right?
Oh, yeah.
So you see me pulling, right?
Mhm.
So if I said y is vertical, or to the left kind of, and x is down, which side is pulling harder right now?
The Y.
Exactly. So that's actually what the data does. So if we look at a data table that matches this, so let's look at data table 2. You've got an x set, which is t, and you've got a y set of data, which is x, which I know is confusing. But x goes right here on your y-axis, and I want you to look at the 2 sets of data. Which one seems to grow faster than the other?
X.
So yeah, these values right here, the meters. So these values seem to be growing faster. And I want you to remember the ruler example. If it's pulling harder, what direction does it bend toward?
The right.
Exactly. So it's going to be bending toward the one that's growing faster. So if they were moving at the same rate, it would be a straight line and it would just be linear. But one of them is growing faster, so it pulls the data toward that right there. And you get a graph that looks like this. All right. So when you pull toward the y values, your curve bends toward the y-axis, and you get a top opening parabola. All right. So let's look at data set 4. So data set 4, I want you to look at the growth rate of both of them. So I want you to look at the velocity, which is meters per second there, or m per s, Does it seem like that's growing rapidly or steadily?
Steady.
So that's steady. So you know it's not going to pull very hard. It's a steady change. Now, what about T? Does that seem to be growing rapidly or steadily?
Rapidly.
It's growing rapidly. So if we're graphing T down here and V up here, which one is going to pull harder, the T values or the V values?
The the T value,
The
sorry.
T values. And so what's going to happen is the curve is going to get bent down. So it's going to pull harder. So this is going to be a side opening parabola. All right, so if we look at our reading, that is the next example that they give you as a side opening parabola. All right, and then your last option for data is if they both increase or decrease together and they both do so steadily. So let's look at data set 3 here. So you can definitely tell that A increases steadily, right? For sure. And then we look at W, and it might not initially show up, but if you look, on average, they're increasing by about 1.5 each time. There's not a huge difference. So this is going to show up as a straight line. And so what you notice is that you get one of each of these graphs for 1 through 4. All right, and then these two down here are repeats, and I'm going to let you figure out on your own. And if you just get it to me by the end of the day, I'll give you that extension. You're good to go, because I do want you to try this. But now, because this is A, wait, is that A? Nope, this is W, so we're going to fix that. W, and this is A. All right, so your goal now is to make everything look like this one. You want a straight line because you want to be able to put it in slope-intercept form. Do you remember how you were able to tell me you had gone 30 feet? You were able to predict how far you went?
Yes, sir.
You can only do that if you have a linear relationship. And so you have to get this graph, any graph that isn't a straight line, you have to do something to the data that's going to correct this and make it a straight line so that you can write an equation that becomes predictable. Okay, so let's first look at this first example. So let's look at what the reading tells us to do with it, because the reading actually tells you how to treat it. So in order to get these values to go in line, they both have to move in the same direction, right? So linear means they both increase, and they both increase at a steady rate. So if one increases and one decreases, I have to turn one of them around. I have to flip them. So let me give you the example here. So I've got data that is increasing here and data that is decreasing there. So I'm going to have to take the inverse, which is 1 divided by these numbers of this, in order to get the numbers to swap around. So let me just show you the beginning and end, and the rest of it's kind of just filling in the gaps. So what is 1 divided by 1/10? How many times does 1/10 go into 1?
10 times.
10 times. All right, let's switch all the way down to the bottom. What is 1 divided by 10?
10.
What's 1 divided by 10?
Can you hear me?
Yeah. What did you say?
I said 10.
1 divided by 10. 1 over 10.
Oh, 5. I'm sorry.
No, it is okay. It is okay. It is 1/10.
I've not done that in so long. I'm sorry.
It's perfectly fine. That's why we do these kind of things up front. So I want you to notice what happened once you took the inverse. The numbers switched, right?
Yes, sir.
They flipped. And so now I want you to watch. So if I'm just going to fill in these data. So 1 divided by 1/2 is 2. 1 divided by 1 is 1. 1 divided by 2 is 0.5. And I'm not going to draw in the decimal points because I have to erase them and they're tiny and it's hard. So I'm just going to I'm going to say what it is. So then 1 divided by 4 is 0.25 or 1/4. 1 divided by 5 is 2 out of 10 or, 0.2. And then 1 divided by 8 is going to be 0.125. So I want you to notice the trend here. As volume decreases, pressure decreases, and now they're moving in the same direction. So now when you plot this new data, you've got 0.1, 0.4, bam. 0.125, 0.5, bam. 0.2, 0.8, bam. And you start to get a relationship that as one increases, the other increases. Do you see this?
Yes, sir. So basically the goal is just to make them always move in the same direction. Like if you find your steady one, and then the unsteady one you make go. Basically, I don't know. I'm trying to think what I'm trying to ask. The unsteady variable is the one that you're manipulating, basically.
You've got it backwards there. Now here it does seem like that. For this example, it seems like that's the one you're going to manipulate. But I'm going to show you for data set 2 and data set 4 in just a second that it's actually the steady one that you make unsteady. And that'll make sense in just a second, all right?
Okay.
So because otherwise you end up having to take square roots of values, and that's a lot harder than taking a square.
Okay.
So
yeah, that's what I ended up doing on my homework, and that's what really confused me.
I can understand that. And so I just want to make one note here, and then this hopefully will make sense. What's that new variable? What did I have to do to get all these new numbers that I plotted here? I had to take the inverse, right?
Right.
That's 1 over v. So my new equation, or my new variable down there is 1 over v.
Mm-hmm.
Now let's look at our reading. And when you make your new formula, you have to plug that in. All right, so this is what makes it predictable. So you're going to plug in 1 over v for x and p for y. So we're going to go ahead and write that. So p is equal to m 1 over v plus b. There's no y-intercept here because we talked about if you don't have volume, you don't have pressure. And let's plug in the 1 over v values. And so we're just going to look at these two values right here. So the slope is y2 minus y1 over x2 minus x1, right?
Right.
So 8 minus 40 is negative 32. 2 minus 10 is negative 8. 32 divided by 8 is 4, and then the negatives cancel. You following so far?
You said 8 minus 40?
8 minus 40 is negative 32.
Okay.
And 2 minus 10 is negative 8.
Okay. Why did you do 2 minus 10?
So do you see this second set of data right here? I've got 10 and then 2.
Yes, sir.
So in this second set of data right here, I'm trying to find the slope of this line right here.
Oh, okay. I got it now. I'm sorry. I was looking at the one that you didn't manipulate.
The original, right. So
Yes.
that's your intuition, and you were correct to think that that's the case. But you got to remember that there's no slope for that line, right? It's curved. So you're going to have to look at this new data to get the slope. You don't have to calculate the slope for this assignment. I'm doing this to prove a point. So if we get 4 here and I plug in 4 and I take any value for this second column and I multiply it by 4, let's see what it gives us. So what's 10 times 4?
40.
Whoa, that's the pressure, isn't it? What's 2 times 4?
8.
What about 1 times 4?
4.
1/2 times 4?
2.
What's 1/4 times 4?
1.
Exactly. So you're starting to see the trend there. This now becomes a predictable graph. And so I could say at a volume, at an original volume of 20, I'd do 1 over 20, multiply it by 4, it will be 1/5. So it would end up being 0.2. All right, so it would be double this. But it becomes predictable in the future. So let's look at data set 2 and then data set 4 really quickly because we've only got about 6 minutes.
Okay.
Alrighty. So you said that X grows faster, so it pulls the line up that way. So for instance, if I've got my ruler and I pull it up that way, how am I going to get it to go back to the center?
You're going to have to pull that back down or release
You're going to have to pull it back down. So you either have to take the square root of the thing that's pulling fast, which is a lot of work, or you square the other one and bring it back down and you make it pull and they both pull equally and then you get a straight line. So what we would do here is we would square all of our t data and it becomes t squared down here and that stays x. And so if you square all of these, this becomes 0.01, 0.04, and this becomes 25 and this becomes 16. All right, I'm just writing that to prove a point really quickly. So your new line is going to look like that. So when you're drawing the second line, you already know it's going to be straight. You just have to figure out which variable you had to square or take the inverse of. Okay, that's really your job here. So just to prove a point here, my new equation is going to be x, because that's the y value, is equal to mt squared, because that's the new treated data, right? Plus b. Now there's no b value here because it runs through the origin. And so I can figure out the slope. 75 minus, actually we'll do this one right here. This is actually easier because that's 4. 2 squared is 4. 3 squared is 9. So 27 minus 12 is 15. Okay, so 15. And then 9 minus 4 is 5. So 15 over 5 is 3. My slope is 3 here. Does that make sense? For this line right here. So if I plug in 3 and take any t value, it will give me any x value. Okay, let's take 5. Okay, what's 5 squared?
25, sorry.
25. What's 25 times 3?
75.
75. And look at that. It immediately told us what our x value is. All right, so you don't have to calculate the slope, but I'm just doing that to show you that this becomes a predictive model. And then let's look at data set 4. And I'm going to assume you can do data set 3 because you don't have to do anything to it.
Yeah.
All right. So which one's pulling harder here? You said it was which variable?
The t.
T. So t's pulling down. So in order to get it to go back to center, what am I going to have to do?
You're going to have to pull it up.
You're going to pull it up in the opposite direction by squaring the v values. These are pretty easily squared. You're just going to add an extra 0 to the normal square of that. So like 10 squared is 100. That's 400, 900, 1600, 2500. And I'm not going to keep going. But what's going to happen is it's going to correct that graph. It's going to bring it there. And which you said you squared v, right? So how are you going to write that here on your axis?
V squared.
V squared. And when you write your mathematical expression, remember that this is your y value. So what's your new y value that you write in here?
V squared.
V squared is equal to mt plus v. And that's your equation. Okay?
I have a question about, I think it was number 2.
Mhm.
Can you just pick any, like for number 1, you picked 8 and 40 and then 2 and 10 to do the slope.
Right.
And then for that one, you picked 27 and 12 and then 9 and 4. Can you pick any of them?
So long as it's linear, that means that the slope is going to stay the same. And that means that the rate of change is the same between any two sets of numbers. I picked numbers that I can do mental math with. So I could have picked 0.12 and 0.03 and 0.2 and 0.1, and then I would have had 0.9 over 0.1. And is that right? Yeah. So 0.09 over 0.1, and it would have given me a really weird number. It would have given me 3 still, but it would have been a lot more difficult to, actually it would have been 0.01 and 0.04 because it would have been the square of these. And that's just extra work. I knew that 2 squared is 4, 3 squared is 9. Those are a pretty easy pair. And so I could have also done these right here in 75 minus 48 and 25 minus 16. And it would have given me the same ratio, different numbers, but it still would have given me 3. So it really doesn't matter, but you will always, if you're trying to determine the slope, you have to pull from the second set of data, the t squared, or else you're going to be pulling from this curve.
Okay.
You got me?
Yes, sir, I got it.
Did that help clear up any questions you had?
Yeah, that actually cleared up all my questions, really.
Awesome. That's definitely what I want to hear. I've gotten better at explaining it with every class. So if you have any further questions, make sure to email me. I hope you guys do fantastic. Let me know how the game goes. And I will see you tomorrow.
Okay.
All right?
Am
So
I good for work or anything? Do I need to do anything else?
So you will just need to make sure that you fill this out now that you know what you're doing, and make sure that you can resubmit it as many times as you need. So just try to get these as accurate as you can, and then submit that for me by the end of tonight. All right, I'll give you a little bit of an extension. And then the last thing is there is a video that will be in the module. I want you to just check it out. It'll be a really nice way to de-stress either before the game or after the game. It is just an introduction to what we're going to be talking about tomorrow with our lab. All right, which is pendulums.
All right. Thank you.
All righty. You're welcome. Have a great day.
You too.
Bye-bye.
Bye.